Hello and welcome to the second installment on this series of Introduction to C++, where we look at the C++ programming language and introduce it by looking at game development on the Raspberry Pi platform. In this installment we're going to look at variables, conditions, loops and lists. And as always, the video tutorial is licensed under a Creative Commons Attribution license. I am Aidan Delaney. I work at the University of Brighton, and on screen you can see some various contact details that you may wish to use if you want to get in contact with me. In the last installment I demonstrated a very straightforward game, not a very brilliant game, but it has some of the features that we want to develop over the next couple of installments. This game is a scrolling shooter, kind of like an 80s arcade game, where you fly your plane or rocket or something kind of thing around the world and blow up these little animated little enemies. First things first though, I want to state some assumptions that I have about who I think I'm talking to and what I'm expecting. One of my assumptions is that you actually have one of these Raspberry Pi computers, either a physical one, or actually you could do a lot of this work on a virtual Raspberry Pi if you emulate the Raspberry Pi hardware using an emulator such as QEMU. I also assume that you have some familiarity with the Linux command line, that you can use standard command line binaries cd, ls and grep, and you're familiar with installing things on Linux, so using the Linux App Store. The other thing to note is that this video tutorial is part of a series of lectures that I give at the University of Brighton. So the video tutorial covers things quite quickly, which may not be suitable for some people. I pair this with an in-class lecture, which it goes into more depth on topics that my students feel are necessary. There are some system prerequisites. If you've got one of these Raspberry Pi computers, it'd be great if you could get the Raspberry Pi version of Debian called Raspbian running on it, and then you need to have a GNU C++ compiler, apt-get install G++. You need to have the SDL and the SDL image development packages. These are on top of the packages you need to run actual games. These are the ones that we need to develop games against. We also need something called libsig C++, which I'm not going to go into at this stage, but I'd like it there on your system. And finally, it would be nice to have a pretty graphical editor, and gedit is my favorite pretty graphical editor, and it would be nice to install that on your Raspberry Pi. In order to have a look at variables in C++, I've opened up a terminal on my Raspberry Pi, and I've also opened up the gedit text editor. So what I'll do is I'll flick between these two. One, I'll write code in the gedit text editor, and two, I'll compile it and run it using the terminal. First things first, I have to write the boilerplate code, the code that one must write in order for the program to run. This is a very simple C++ program. It must have a main function, which takes no parameters and does nothing except returns 0. The C++ standard says that any C++ program must have a main function, and it must return an integer, in this case in 0. I'm going to save that. Hopefully it'll bring up a prompt, and I'm just going to call it something nice and simple like variables.cpp. Please select a folder. Oh, my home folder. I'm the Pi user. And as you can see, one of the reasons I like this text editor is because it then will give me some nice syntax highlighting. Okay, so in C++ we've got many variable types. The first of which is the car variable type. Car, in this case I'm going to declare a character of type called C, and I'm going to initialize it to store the character A. Cars are interesting from the point of view that they are the basic unit or type in C++. They are 8-bit long and they're used quite extensively. The other interesting fact about characters is that they don't quite operate like characters that you in a natural language, or as you would expect in a natural language. They're quite suited to storing English as a natural language, but as soon as you go off into other natural languages, for example French, Polish, and certainly into the Chinese and the CJK languages, the Chinese, Japanese and Korean, cars are just completely unsuitable for storing characters in those languages. So I introduced them here as the basic type in C++, being 8 bits long or 8 bits wide. We've got our int type. Ints store whole numbers, such as -1. We've got the bool type. Bool represents the choice between either a true or false value. In this case I'm going to initialize it or set it equal to true. A boolean type called B, I'm going to set it equal to true. And we also have a float type, which stores floating point numbers. Float f is equal to -1.0 f. And again, because I like to, I'm going to align these things correctly. And a floating point value, whereas an integer value will store something with a whole number, a floating point value stores the decimal place numbers. And a double, which is quite similar to a floating point number, except it has double the precision of a floating point number. Now, what does precision mean? In essence, floats and doubles are very, very useful data types for handling measurable physical quantities. They're both, kind of hand-waving here, accurate up to about 5 decimal places. You would not use them for storing values in a financial application which needed exact values. So we've now got ourselves a program which declares a character, it declares an integer, it declares a boolean value, it declares a float, and declares a double. So what we can do is go ahead and compile that. As in the last installation, we said that C++ has a 2-step compile process. I'll ask my G++ compiler to please compile me the file called variables.cpp. And I'm also going to tell it to use the newest version of the C++ standard. Standard is C++ 0x in this case. So that's going away. It's compiling my variables.cpp file. Now I want to create an output file called variables. And from variables.o, it's taking the compiled file and linking it against the system implementation of lots of things, and then creating the runnable file, the runnable executable called variables with a lowercase v, just because I chose a lowercase v. So let's run this, and unsurprisingly it does nothing visible. It is running this main line. It is allocating a character, it's allocating an integer, it's allocating a boolean, it's allocating a float, and it's allocating a double, and then it's exiting. Now, often what we want to do is actually see those things printed to screen. In the case of C++, what I want to do to print those to screen is pull in the IO stream. Include IO stream. The header file, as it's called, inside these angular brackets. Then I want to use cout. I want to direct, for example, the character C into cout, and I want to end the line. Now, cout and endl are defined in a namespace called standard. This is just boilerplate, so using namespace standard at the top of C++ programs at the moment until we understand what it means. Well, I'll save that. We'll switch to the terminal. We will try and compile it. At this stage, if I had made syntax errors, the compiler will pick them up. And what we can see is that I haven't made any syntax errors. I'm going to link that into the variables executable. And before I execute it, I'm just going to have a look at that code again. And what I expect to happen is that the character called C will print out to screen. What happens is that this cout is where the C gets directed to, followed by an endl, which in this case is a symbolic definition of an end-of-line character. So I expect to see the A character printed to screen and followed by a new line. So let's run that. And that is exactly what I get. I get an A character printed to screen and then a new line. Nicely in C++, what we can do is add more things to this output stream. I can add a space, and I can also then print the integer character, or the integer I. So what this should do is turn the integer I -1 into a sequence of characters and then print them out to screen. Let's try that. We'll compile it. Hopefully I haven't made any syntax errors. And we will then link it. And finally, before I run it, I'm just going to check to see what I expect to see on screen. I expect to see an A character stored in the variable called C, then a space, and then -1, which is stored in the variable called I. Great, exactly as I expected. It's interesting to print out these double and float values. What I've got to do is just remove the D there, at the I there, and print out that double value. And I've got to remove this C here and print out this float value, because what I said to you was that they were useful for storing physical quantities. And you can see there's a difference between them, is that one is declared with an F at the end, the other one is not declared with an F at the end. Double is twice the precision of a floating point value. Again, that's a general rule rather than a hard fact. These things are platform dependent, or dependent on the standard that's been implemented in floating point. Let's compile that again. And then we will link that when that compiles. And we will run this. And when I run this, I expect to see -1 get printed out to screen twice, which is quite boring. However, let's try something slightly more interesting. Let's initialize the float f to be -1 divided by 3.0 f. And similarly, the double -1 divided by 3.0. In both cases, what we're representing is a third, or 0.33333 recurring in decimal. And what we should see then, printed out to screen, is something like 0.3333 to about 5 decimal places. We'll compile that. We'll wait for it to compile. Then again we will link it. And finally we'll run it. So I see, because I divided -1 by 3 in both cases, I expect to see -0.333333 to 6 decimal places in both cases. Now, what's very interesting is if I use a count.precision, if I set the precision to being very high, so print out 20 decimal places for each of the float and the double, and recompile that. And again, when it's compiled, we're going to link that program against the system implementations of cout and endl, and then run this. You can see that the floating point value, after approximately 7 decimal places, introduces significant amount of error. This should be 0.3 recurring forever. whereas a double value takes an awful lot more decimal places before it starts introducing error. That's what I mean when I say that the float and the double values are designed to measure physical quantities rather than exact, for example, financial quantities. Again, we'll take this out of here. Another way of declaring or initializing variables in C++ is, rather than using this assignment operator, is to do as such and use effectively a construction. This again should do exactly as we expect. In order to check this, I will ask my compiler to compile it. It will pick up any syntax errors that I make. I have not made any. Then we'll link this, and I will expect it to print out minus 0.32, 3 recurring to 6 decimal places twice. Great. One of the other standard things that we can do with particularly the integer type, which is often used in programming, is apply standard operators to it. So I can say that I is equal to I plus 3, which takes the value in I and adds 3 to it. We'll print that out to screen, save that, flip to a terminal, compile it, and then link it when the compiling is finished, and then finally run it. In this case, if I take -1, if I add 3 to it, I'll expect to see 2 printed to screen. Great. My maths isn't strong tonight. Similarly, I can subtract numbers from it. So I is equal to I minus 3. So if I take the value that's in I, take away 3 from it, and then reassign that to I, I should then hold the value -4. -1 was in I, then I take 3 away from it, -1 minus 3 is -4. Link that, and then execute. Excellent. All is as I expected. We've already seen that we can use this / operator to divide, in this case a double, and in this case a float. We can do the same with integers. In this case it's going to be -1 divided by 3. That should be -1 divided by 3 is -0.33333 recurring, as we've seen. But in this case, an integer can only store whole numbers, so the output is going to be, as we call it, truncated. You're only going to get the integer part of that. You're not going to get anything that occurs after the decimal point. So the integer part is 0. And finally, after we've seen addition, subtraction, division, we're finally looking at this star operator, which is multiplication, or how one will write multiplication in C++. -1 multiplied by 3, compile that. If we multiply -1 by 3, I would expect to see -3 printed on the terminal. Link it, run it. Fantastic. So, quite quickly what we've seen is that I have written a very small main line. I have introduced a character type, an integer type, a boolean type, a floating point type, and a double type. We've also looked at how we can use output operators, cout, the 2 angular brackets directed at that, and to print things to screen. We've then had a look at compiling this, linking it, and running it. Now we're going to have a look at conditional statements in C++. In order to look at conditional statements, I think it's nice to have some kind of scenario, a simple problem that we're trying to solve. And what we want to do is make a decision. And in this scenario, we're going to assume that we've got 2 teams which play a game where the score can be represented as an integer. Now, it's immediately obvious to an experienced software developer that this is quite restrictive, but we'll go with this scenario anyway. It's restrictive because it can represent scores like in a game of rugby, where a team scores 15 points and the other team scores 20 points, or it could represent a score like in golf, where somebody is +4 or 4 under par, or it can represent the scores in a game like Quake, where the scores are the number of kills that one gets. It can't represent scores in a sport like tennis, which are or racket sports in general, badminton or table tennis, where the scores are actually in sets and games. It can't represent the scores in Gaelic football. It can't represent the scores in cricket, which are based on wickets and runs, and in very weird and wonderful cases, the Duckworth-Lewis score mechanism. But what we want to do is represent in our game a variable that stores the score of Team A, a variable that stores the score of Team B, and we want to decide in our game which of these two teams has won. Again, I open up my text editor on my Raspberry Pi. I'm going to start a new file this time, and I'm going to call this, save this as, and I'm going to call it Conditionals.cpp. The CPP meaning C++ as an extension to the file. I'm going to do the same thing I did last time, include IO stream, so that I can print things to screen. INCLUDE, and I'm also going to be using namespace standard. Going to define a main line, int main taking no parameters, and from this main line I'm going to return 0. On my operating system, on the Raspberry Pi operating system, if a main line returns 0, it means that the program executed with no errors. This is very operating system dependent, but of the major operating systems on the market, Linux, OS X and Windows, all of them define 0 as their return type of a program that has no errors. Okay, so in this case I'm going to declare two new ints. I'm going to call one of them Team A score, and I'm going to initialize that to 10, which is straightforward. Then I'm going to declare one called Team B score, and I'll initialize that to 11. Now, we can write comparisons between these two variables. I can ask Team A score, is that greater than Team B score? Which is a valid statement in C++. What we will do now is compile this, G++ -C conditionals.cpp minus standard equals C++ 0x. Again, that will take time to compile. I haven't made any syntax errors. I now want to link that -o conditionals with lowercase c, just because I wish to, and I want to take the output file of that and link it, and then run conditionals. Incredibly boring. We haven't put anything to screen, but what we have done is written a valid C++ program. I've used the greater than sign here to compare Team A, the value in Team A score, with the value in Team B score. It would be nice to ask if Team A score is greater than Team B score. If it is, do something. If Team A score is greater than Team B score, I would like to cout, and in this case I want to output a string in double quote marks, Team A wins. Now, we can see that team A score is not greater than team B score. So when I compile this program, and then subsequently link this program when the compilation returns, and then run this program, I expect it to print nothing to screen. I want to check if team A score is greater than team B score, then print team A wins. In the other case, else if team B score is greater than team A score, cout team B wins. Again, notice the syntax that I'm using here. I first state the keyword if, then I put the condition that I'm going to test for inside parentheses, these rounded brackets, and I use some kind of comparison which takes, in this case, two integers and will give us back a true-false value. Either team A score is greater than team B score or it's not. It's either true or false. If this is false, then we'll say otherwise evaluate this. Is team B score greater than team A score? In this case they are. Team B score is greater than team A score, so we expect the output of this program to print team B wins. So we'll compile it as we normally do. We will then go and link this program, and finally we'll run this program, and it says team B wins, which is great. So we now have a program that if we give it to integer values for team scores will tell us which of these two teams wins. Unfortunately, there is a logic error in this program. If team A score is greater than team B score, we get an output. If team B score is greater than team A score, we get an output. However, there is a case where team A score is not greater than team B score and team B score is not greater than team A score. And this is where the scores are the same. I'm going to verify that there's a logical error in this program by setting the scores to being the same and seeing that there's no output from this program. I'm going to compile it again. Compiling always takes a certain amount of time. The larger your program, the longer the compile. Link it together and then run it. And as I expected, there's a logical error. There was no output from this program. So finally, if neither of those two conditions are satisfied, I'm going to say else. If neither of those two conditions are satisfied, I want to see out there was a draw, which is the general sporting term to mean that the teams have both the same score. So now, if I compile my program again, and then after compiling returns, I link it, and then when I run it, I expect to see that there was a draw between the two teams. Great. So at this stage we've written actually a relatively complex application which makes a decision and will output a string, output something to the terminal based on the input values to the program, or the hard-coded values in this case. In order to demonstrate lists in C++, I've created a lists.cpp file which contains a skeleton program or a boilerplate that we're going to use, which includes the IO stream header, the mechanism for printing out to screen. It's declared that we're using the standard namespace, and then a main line which simply returns 0. In order to use lists, I have to pull in lists from the C++ standard library, more properly called the standard template library. Include list. Then, somewhere in my main program, I can declare a list, a new list. this case I've declared a new list, and I've got to tell it that it stores integer types. And in this case I've declared a new list called L, which stores integer types, and I'm initializing it to storing the integers 1, 2, 3 and 4. We can compile that and then afterwards link it when the compilation returns, and finally run it to find that it does absolutely and utterly nothing. In order to do something with this, what I'd like to do is print each of the elements in this list to screen. What I have to do is get the first element in the list, then get the second element in the list, then get the third element in the list, and then get the fourth element in the list. And each time I get an element, I want to print it to screen. To do this, I need to introduce the concept of iteration. So we have our list defined in C++. What I would like to do now is get each of these elements from the list and do something with it. C++ 11 provides this very nice syntax for int I, so for an int called I from the list, do something with it. In this case, what I'm going to do is cout I, and put each one of these on its own separate line. So what I'm asking it is, for each integer in the list, do something with that integer. We will compile that program. When it returns, we will link that program, and what I expect the output to be is quite simply 1, 2, 3, 4, all on separate lines. Great. So what we've done is simply defined a list containing some integers, and what we've done is iterated over that list using a very nice syntactical construct in C++, which allows us to pull out each integer from the list and do something with it. In conclusion, what we have covered, actually very, very quickly, on the Raspberry Pi and under the idea of developing games for this is variables in C++. We've covered some console output in C++. We've covered conditional statements in C++, this idea of if, then else if, and then finally else. We've had a very quick look at lists in C++, but we've not manipulated them very much. And we've had a very quick look at iteration in C++, particularly the idea of getting information out of a list and doing something with it. Finally, again, I'll note that this is all a brief summary of what's covered in my class at the University of Brighton on game development in C++. I'd like to thank you all for listening.